So in this video, we are going to discuss the second part of counting, which includes the two concepts of permutation and combination. So again, the reference can be obtained from the following chapter in a textbook, which is provided to you on eLearn. In particular, for permutation and combination, it can be found in the section 6.3. So we begin with permutation. So what is permutation? So when we talk about permutation, we usually talk about a number of objects, and we want to order these objects in a particular sequence. So a permutation essentially is a way to sequence a set of objects. Now let's look at a particular example. So here on the left half here, we are given a set S which includes A, B, and C, three objects. So then we can talk about all the different permutations of A, B, and C. And this includes A, B, C, which means that A comes first, followed by B, followed by C. Or A, C, B, in which case A comes first, followed by C, followed by B. And then essentially you have all six permutations there with BAC, BCA, CAB, and CBA. Now, if you're given another set T, which contains a different set of objects, 1, 2, 3, again, we can generate different permutations in terms of the different sequences. Now, how many such permutations can exist for any particular set of length n? So we denote this number as n factorial. And we can actually think of this in terms of an application of the product rule. So if you are trying to give a particular arrangement of objects, essentially we are trying to find out what should come in the first place. Now if there are n objects, there are n possibilities of things that can come in the first place. And then you have the second place, which will have n minus 1, and then the third place, which have n minus 2, all the way to 1. So n factorial essentially is n times n minus 1 times n minus 2 times n minus 3 all the way to 1. Now this is when we talk about the permutation of all n objects. Sometimes we are interested in a permutation only of a subset of the objects. And in this case, in this slide, we talk about an R permutation of n objects. And we usually denote this as NPR, which means that permutation of R out of n objects. Now in this case, we can see that we are not trying to arrange all of the objects, but rather only a subset of them. So now given the same subset, S equals to ABC. So if you're interested in two permutations, which means the permutations of any two objects, it will include AB, AC, BA, BC, CA, and CB. Now, how many such permutations will there be? Now, we can think of this in terms of an application of a product rule. So for example, given a set of S equals to ABC, so if we are looking at a permutation of two objects, so then we need to figure out what should come on the first place, of which there are three choices, A, B, or C, and what should come in the second place, of which there are two options, because we have taken one in the first place. So in that case, we have 3 times 2, which is 6. Now, you can also apply the formula that is given at the bottom of the slide, where it says that the number of R permutations of a set of length n is NPR equals to n factorial divided by n minus R factorial. Now, let's look at an example. So right now is the season of the Olympics, and in this case, there are 150 countries. They are competing in the Olympics. Now, how many ways are there to select first place, second place, and third place winners? So we can reason it out in terms of the product rule. So in this case, for the first place, there are 150 choices, because any country can be the winner. Now, the second place, we only have 149, because the first place cannot also be the second place. And in the third place, we have 148. So by product rule, we're going to have 150 by 149 by 148. So this amounts to 3.3 million. Now, we can also plug it into the formula, in which case we just put in 150p3 equals 150 factorial divided by 150 minus 3 factorial, in which case you're going to get essentially the same number. So the second concept is that of combination. So for combination, we are interested in a set of objects, but we don't particularly care about the ordering. So which means we only are interested in what make up the set, but we are not interested in what is the order or the sequence in which they come. So supposing that we have a set S equals to ABC, now the combination of items in ABC would just be ABC itself. Now, ABC or BAC or CAB, these are all considered the same combination because we don't particularly care about the sequence. Now, in that case, a combination of a set of length n, there is only one, which is the whole set itself. Now, but again, sometimes we are interested in not the combination of all, but a combination of a subset. So then we have a concept of R combination of a set of n objects. So in this case, we are talking about an out-ordered selection of R objects out of n. So given a set S, A, B, C, the two combinations are AB, AC, and BC. Now, AB and BA are two different permutations because in permutation we care the ordering in which they come. But AB and BA are the same combination because we don't care about the ordering in combinations. So now if we think about the number of ways that we can select a combination of R items out of n, is given in the formula below, which is NCR equals to n factorial divided by R factorial times n minus R factorial. Now, if you notice, the formula is actually kind of similar to the NPR from permutation earlier. The difference is that essentially this is another division by R factorial. And the reason why that is that once we are given a particular permutation of objects, then any permutation of that set will give us the same combination. So we can divide by R factorial. Now, this is going to be clearer through an example in the next slide. So if there are 150 countries to compete in the Olympics, how many ways are there to select top 3 winners if you don't care about a specific ranking? Now, on the left-hand side, we're going to reason through permutations. So first we generate all the 3 permutations. So 150, 149, 148, this is 3.3 million. Now, for any 3 items or 3 objects, there are going to be 3 factorial different ways to permute them. So in the case of ABC earlier, we have ABC, ACB, BAC, BCA, CAB, and CBA. There are 6 permutations. But the 6 permutations are referring to the same combination. So if we want to know what's the number of combinations, then we look at the 3 permutations, and we just need to divide this by the number of ways in which we can permute 3 objects, which is 3 factorial. So if we do this, so we get 3.3 million divided by 6, so it'll be 550,000. Now, we can also just plug it into the formula, in which case we have 150 choose 3 equals 150 factorial divided by 3 factorial times 150 minus 3 factorial. So we are going to still end up getting the same outcome.